In this session, I am going to demonstrate the need to address an imbalanced dataset and how to address an imbalanced dataset. I am going to be explaining this using predictive maintenance. We are going to be developing a machine learning solution for predictive maintenance, and as part of it, we are going to address the imbalanced dataset. Okay. Predictive maintenance comes under industrial analytics. That is, in factories and industrial establishments, maintenance managers and factory managers would like to know ahead of time, of course, when machines are likely to fail. This is a sea change from the earlier approaches of preventive maintenance. Factories and industrial establishments have been doing preventive maintenance. We do preventive maintenance for our automobiles, like cars, bikes. We do preventive maintenance, right? But what if we could know when our automobile vehicle is going to fail? That is predictive maintenance. This predictive maintenance is finding adoption in many industrial establishments, because if an organization knows when an equipment is likely to fail, they can take appropriate actions and ensure the continuity of the organization. Today, it is not just predicting at an overall equipment level. We can predict when a particular part in an equipment will fail. That level of granularity is now possible thanks to machine learning. And using predictive maintenance, I have seen that the instances of downtime, especially involving critical equipments, can come down by as much as 2/3, even in the first year of implementing a predictive maintenance solution. It can work alongside other techniques like non-destructive testing and process control. Okay, very simple one, right? Because this can be easily used by anyone. I'm talking about using the output of the modeling exercise. Of course, for the modeling exercise, you need statistical and programming knowledge skills. But to use the output of a predictive maintenance algorithm, anyone can make use of it, right? Because you will know when the equipment is likely to fail, and as a factory manager or a maintenance manager, one can take appropriate actions, right? Predictive maintenance particularly useful in cases involving prediction of low frequency, high impact failures. Because in many industrial establishments, failures happen rarely, but when it happens, the impact is higher, right? That is what I mean by low frequency, high impact failures. So this predictive maintenance analytics, okay, is very helpful in determining when certain parts in an equipment will fail. This information can be used by the factory managers and preventive maintenance team to take appropriate action. In fact, the predictive maintenance is one component of Industry 4.0, right? Many organizations are adopting it and getting very good benefits out of this. So let's see an example of predictive maintenance in action. Okay, this data set comes from UCI. Okay, the data set contains about 10,000 records and 14 features, right? There are 339 points belonging to failure and 9,661 belonging to no failure class. This means the data set is highly imbalanced. The number of data points pertaining to a failure information is very low, right? This is what I mean by an imbalanced data set. When you have an imbalanced data set, the imbalance needs to be addressed. If the imbalance is not addressed, your model will take a beating, because your model will predict that no failures are possible, because the number of failure points is very low, because the model is looking for patterns, right? So here the patterns is overwhelmingly in favor of no failure. So that is the imbalance which needs to be addressed, right? So these are the fields that are there in our data set. Okay, there are no missing values, which is good. We know that the columns, right? Tool wear failure, heat dissipation failure, power failure, overstrain failure, random failures. These represent the different failure modes that can happen in a machine. If any of the 5 columns is one, that is, a failed scenario, the machine failure is one. That means the machine is failed. If any one of the failure happens, it means the machine has failed, right? So therefore, for the purpose of this model building process, we will take the machine failure column as the target column, right? We will then scale the data using min-max scaler and encode the nominal data using label encoder, right? Is this clear up to this point? Okay. Now let's come to the imbalanced dataset, because this is something very characteristic of predictive maintenance. Low frequency, high impact failures, right? The percentage of instances belonging to failure class is only 3.5%. This is very, very low, right? It will result in poor predictions. No doubts about it. So the balance needs to be established, right? So for this purpose, we will use a library, right? We will use random undersampling and SMOTENC, right? Synthetic minority oversampling technique for nominal and continuous variables, right? There are different libraries available to address the imbalance. Okay, why we are doing it? We are doing it so that the data set is balanced. Only then the model will be able to predict the likelihood of failure events, right? So this is very, very important in predictive maintenance model building. Please keep this in mind. Okay, so this synthetic minority oversampling technique is used for oversampling the minority class, that is the failure class in our data set. It works on the principle of k nearest neighbors. This is PLE, not PAL, principle of k nearest neighbors. Okay, and random undersampling. It's a technique used to reduce instances of majority class, that is the no failure class, right? If we adjust only the minority class, it will still be biased, right? Because we have not adjusted the majority class. We must adjust both the minority class as well as majority class, right? So random undersampling removes instances from the majority class, and this is done in a random manner, right? By removing the necessary points, the integrity is maintained. Please note that. Okay, so using SMOTENC, okay, the minority class is adjusted to have 25% of the initial number of majority class. Using undersampling, okay, the majority class is adjusted to have 50% more values than the minority class. Okay, so let's look at the actual numbers so you understand this 25% and 50% clearly, right? Before adjusting the imbalance, the failure class was just 3.5% compared to 96.5% of no failure class. The imbalance is adjusted now, okay, thanks to SMOTENC and random undersampling. We now have 33% of failure class and 66% of no failure class. Clear? The before and after scenario can be seen very clearly in this graph, right? The imbalance has been addressed and we are ready to apply the model. Okay, and the algorithm that we will use is HPOS, histogram based outlier score. Okay, you can apply any of the outlier detection algorithm, right? But here, since the distributions are close together, we can use any of the proximity based algorithms, right? And HPOS is a good proximity based algorithm. Okay, the algorithm works by building histogram for each feature, and scores are calculated individually. Okay, the histograms are combined together in the end. Okay, so the ones that you see at the extremes, these are the outliers. Okay, in the world of histograms, these are known as bins. So there are 3 bins, and the height of the bin is this much, and the height of this bin is this much, and the height of this bin is this much. So the information pertaining to the number of bins and the height of each bin is also used while arriving at the individual score. Okay, which is then consolidated and we find the outliers. That's how the histogram based outlier detection works. That is, in a histogram, if you see this histogram, the ones that are at the left and the rightmost end, these are outliers. This is the histogram for temperature. That is, temperature is looked at individually. Like this, we look at different aspects of the data and then we consolidate towards the end. So we compute a score for each of the records. Clear? The algorithm has an accuracy of 65%. As I explained in the session on PyOD, please look at accuracy from both outlier as well as non-outlier perspective, because both are important and we want to have a higher forecast accuracy both in the outlier population as well as in the non-outlier population. Right? Now let's go over the codes that we use to arrive at the results. Right? The first step is installing PyOD. Right? Along with that, import NumPy, Pandas. Right? The 2 libraries that we use extensively in the world of machine learning. Along with that, import Matplotlib and Seaborn. These are used for data visualization. We then read the data set. Okay, we pre-process the data set. We check if there are any null values. Then we scale the numerical columns using min-max scaler, and then all the non-numeric values are encoded using label encoder. Right? These are very, very essential steps. We complete that, and then we plot the unsampled distribution. We then adjust the imbalances using Smotenk and random undersampling. Okay. Then we plot the sampled distribution. We saw that before and after scenario, right? That's what I am doing here. I first plot the distribution that exists with the imbalance. I adjust the imbalance and then I plot it again to see the before and after scenario. After this, I create the model instance. Here I am giving a contamination percent of 33%. You can give a 40% also, or a lesser 25% also. Play with it, right? Entirely up to you. And then we fit the model and we evaluate the results, right? So this is how we go about building the model for predictive maintenance. Predictive maintenance model is very similar to other types of models in other scenarios like churn prediction or fraud detection. But the key characteristic or the defining characteristic in a predictive maintenance data set is the presence of imbalanced data. The imbalanced data must be addressed. Only then your results will be accurate. See, this is very, very important, right? You have large equipments. The cost of repairing those equipments is prohibitively high. So you don't want to make mistakes. Do you understand? If you make mistakes, there is a financial impact. So if you don't address the imbalance, you are actually causing a financial loss to the organization. We don't want that, right? So address the imbalance, then build the model, assess the accuracy.